These expressions are all approximately true for all real stringed instruments. They're not exactly true, but they're very, very, very close. All right. So it's a useful sort of thing to look at. So then, how does this relate to the guitar or any stringed instrument? Well, when I pluck a string on the monochord or on the guitar or whatever, I'm exciting all frequencies, because this pluck is a very transient action, right? Just like, pounding on something that's transient. So I'm essentially, it's impulsive. I'm inputting a lot of frequencies. All right. The string will respond at the frequencies that it likes to resonate at, and these are the ones. All right. So if we look at, I want to erase this. If we look at the spectrum of the sound from a guitar, we would expect that the frequencies that we get, which form peaks in the spectrum, to be high at those frequencies that we just calculated. So if we look at a graph of, this is going to be amplitude, and this is going to be frequency, all right, on the x-axis, we would expect that our first peak would be right around F1, and that our second peak would be right around 2 times F1, which is F2, and that we would have a very regularly repeating or evenly spaced spectrum of peaks. All right. But what's interesting is that this spectrum here is like a recipe for how the sound sounds, and what the spectrum is most closely tied to is the timbre of the sound. So you can change the amplitude of a sound and not change the note, and more or less not change the timbre either, right? So that's, it all sounds like a guitar plucked on the high E string, right? You can change the pitch and not change the amplitude, and you're just changing the pitch. But you can change how you excite the instrument, and you get, even if you have the same amplitude and the same pitch, you can have different timbre. All right, and sometimes it's subtle, sometimes it's really, really dramatic. If I pluck where I normally pluck on this low string, I get something that you would recognize as a guitar. If I pluck up here, it might sound a little different, but it's a little subtle. All right, but if I pluck really close to the bridge, there are parts that are very different, and it kind of depends on if you put it, if you start playing chords down there, that would sound a lot different than if I'm playing it up there. All right, so same amplitude, same pitches, but different timbre, and it's because of how I'm exciting it. So on some levels, it's kind of subtle, but there are other methods of exciting the stringed instrument where it's not so subtle. So if I play let's see if I can play a chord. It's almost in tune. All right, that sounds reasonable. But then if I change how I excite it, you get a different timbre, right? I'm using a little device they call the Jellyfish, and it's one of these gizmos you can get to make your guitar almost kind of sort of, if you close your eyes and imagine it, sound like a 12 string. But the point is that a different excitation will lead to a different initial condition for the string, which leads to a different spectrum here. All right. Now, if you look at a guitar, most pluck stringed instruments, most of the time you pluck the string about 1/5 of the way from the edge. Okay, and it turns out that if I pluck at about 1/5 of the way from the bridge, I end up de-emphasizing the 5th harmonic. It almost completely goes away, whereas the 6th, 7th, and 8th would still be there. All right, and then every 5th harmonic is going to be gone. If I pluck at the halfway down, I get rid of every other harmonic. I get rid of the odd or the even harmonics. Okay, and it turns out for because of how the guitar is tuned, it actually is advantageous to get rid of that 5th harmonic. It helps the guitar sound like it's more in tune, for at least for standard tuning and so on and so forth. But that's just one of the considerations that goes into the timbre. So I want to. Okay, I want to talk about 2 other things, and we'll actually talk about the instrument that we can build. And one is that I want to go back to the idea we were talking about at the beginning, where the string itself is coupled to the rest of the instrument. All right, and we just talked about the resonances of the string, but it turns out that the body of the guitar, the top plate of the guitar, and the rest of the guitar have their own resonances. And the resonances of the top plate itself, they're very complicated, and I'm not going to talk about what they are specifically, but they resonate at different frequencies, and they're not harmonic like the string is. The string is harmonic. That means these frequencies come at integer multiples of the first one, but the resonances of the top plate, for example, are not harmonic. But we can figure out what they are. We can experimentally determine what they are. But those resonances are, well, I should say that I don't think there's a luthier alive that should claim or can claim that he or she can tune every resonance of the instrument to exactly what he or she wants. I mean, they can get them kind of in the ballpark and get them close to where they should be, but every piece of wood is going to be slightly different, and so tuning every resonance exactly is going to be impossible, and more so than that than ever questioning the quality of the craftsmanship of a luthier, is that those resonant frequencies aren't going to line up with every single note that you want to play. So if I have a frequency, a resonant frequency of this that's around, say, 420 hertz, should I not care that that doesn't line up with the 440 hertz of the A that I want to play? Well, it turns out it doesn't matter, because the mechanism that we were talking about earlier, where the soundboard pushes more air, that's not a resonant mechanism. What we call that mechanism is we call it sympathetic vibration. So I pluck the string vibrates at all those frequencies based on its length and tension and the mass, right? And it will shake the bridge at those frequencies, and that the soundboard will shake at those frequencies. And so we're not causing the soundboard to resonate when we couple the vibrations from the string into it. Even though we are causing the string to resonate, we're causing the soundboard to vibrate at the frequencies that the string dictates. And so, but of course, the resonant frequencies of the rest of the instrument, they act as a filter on top of the the vibration of the strings, so they can also go into shape. It's not a strong effect, but it is an effect there.